Good evening, guys, and welcome to our last lecture. This will be the last topic that we talk about in this class. So, if you have any questions, comments, problems, anything that's bothering you, please let me know. If that is not the case, then let us begin the last thing that we're going to talk about. I'm going to go ahead and share my screen, and then we will do as we always do and start our slideshow. Again, this is going to be a fairly short lecture. We're not going to talk about too much here. And I'm going to do preparation for the third exam and the final so that you guys can see that. Like I said, I will do my best to put together practice for each topic as well as the final. But I don't know if that's actually going to happen in a time that's useful for you guys. So you will get some practice with this moving forward, I promise. We're going to talk about chapter 17. This is sections 1 through 6. So while we're technically only supposed to talk about Gibbs free energy and chemical equilibrium, I didn't feel like it worked very well unless we talked about the, beginning of thermo and spontaneous processes and entropy and, all the rest of this. So we're going to go through all of that before we get into Gibbs free energy and chemical equilibrium. Okay? So let's get started. So the laws of thermodynamics. First law, energy cannot be created or destroyed. We've talked about this a little bit. Second law, for a spontaneous process, entropy of the universe increases. Okay, and the third law, a perfect crystal at 0 Kelvin has 0 entropy. Now that has to be a perfect crystal, but we'll get back to that. Entropy will be defined shortly. Okay. Spontaneous process is a process that will happen without any intervention, that will not undo itself in nature without intervention. So the reaction is spontaneous in one direction, but not in the other. And what determines if a reaction is spontaneous? Well, we've talked about a number of things that we said were related to the spontaneity. So the change in heat, the enthalpy changes. So generally speaking, exothermic reactions are spontaneous. They give off heat to the universe. They are generally more spontaneous than endothermic ones, but not all exothermic reactions are spontaneous, and some endothermic reactions are spontaneous. We also have the change in order, which is the entropy changes. So entropy is a measure of how spread out or dispersed the energy of a system is among the different possible ways that a system can contain energy. So the greater the dispersal, the greater the energy. So one of the ways that we talk about this is how much disorder can the system have. So something in the liquid state has many more abilities of ways that it can arrange itself than a solid state does. So the liquid state has a higher entropy. Okay. So entropy is a way of measuring the disorder of a system, how random that system is. The more random it is, the more favorable it is. And that is a better entropy state. Okay. Now, entropy, it's not possible, or it is possible, to measure absolute entropy. Standard entropy is the absolute entropy of a substance at 1 atmosphere, and usually quoted with its value at 25 degrees C for 1 mole of substance. It can be listed as either joules per Kelvin or joules per Kelvin mole, but the value is for 1 mole of substance. Entropies of elements and compounds are all positive. More complex molecules have higher entropy values because there are more ways that it can exist. Gases are less ordered than liquids, so that means the entropy values are higher for gases compared to liquids. Heavier atoms have a higher entropy because there are more ways to organize the nuclei and the electrons in that, so those values are larger. Okay. Now, entropy for the universe increases in a spontaneous process and remains unchanged in an equilibrium process. For a spontaneous process, delta S for the universe, which is equal to delta S for the system plus the delta S for the surroundings, is greater than 0. For an equilibrium process, the delta S equals those two, and it has to be greater than 0. has to equal it. So if the delta S for the system is negative, the process is not spontaneous in the direction described. It's spontaneous in the opposite direction. Entropy changes can be calculated in the exact same way that we talked about calculating enthalpy changes. Okay, so the sum of the number of moles of the products, the delta S for the products, minus the sum of the number of moles of times the delta S for the reactants. Standard entropy values are given in the exam handouts on page 10, table 17.1. If the value you require for a calculation is not in the table, you should be given the value on the test. If a reaction produces more molecules of gas than it consumes, delta S is greater than 0. If the total number of gas molecules goes down, delta S is less than 0. There's no net change in the number of gas molecules, then delta S could be either, but it'll be very small. Okay? So those are some of the generalities that we have about entropy values, right? Now, reaction enthalpy and the entropy of the surroundings. If the enthalpy of a reaction is negative, so if it's exothermic, heat is given off to the surroundings, then the disorder in the surrounding goes up. So the entropy goes up and is therefore positive. Okay? So if the enthalpy of the reaction is positive, it's endothermic, heat is taken from the surroundings, then the disorder in the surroundings goes down. So the entropy goes down. Okay? So if I've taken heat away from the surroundings, it has less disorder in it because there's less kinetic energy. And so that's how that works. Okay? Now the entropy of a perfect crystalline substance is 0 at absolute 0 of temperature. But that's only true if it's absolutely perfect. So if there are impurities in it, that creates a level of entropy. Okay? All right. Questions, comments, problems about anything we've talked about so far? Hopefully not. That's just the background information to be able to get us to talk about the Gibbs free energy. So if my main goal is to predict if a reaction will occur or not, then both enthalpy and entropy are not sufficient for me to do that. So negative T delta S for the universe equals delta H minus T delta S, where that's less than 0 for a spontaneous reaction. We can rewrite that as delta G equals delta H minus T delta S, where delta G is Gibbs free energy, the energy available to do work. For standard states, this is the same, but it's not always 1 atmosphere, the things that we've talked about. 1 atmosphere, for the gases, 1 molar for the aqueous components. So the equation is the same, we just don't have the standards. This is calculated in the exact same way that delta H and delta S are calculated. We can calculate this in the same way, right? So standards again, 1 atmosphere pressure for gases, pure liquid, pure solids, element delta G, F, standard equals 0. Solutions are 1 molar in concentration. Now, let's take a look at the 4 cases that we have. So if delta G is made from delta H and delta S, then we have some conditions where it's always favorable, some conditions where it's never favorable, and some conditions where it depends. So if delta H is positive and delta S is negative, so it's endothermic, I have to put energy in, and the entropy is not favorable, then delta G is always positive. The reaction is spontaneous in the reverse direction at all temperatures. So the way that it's written, it's never spontaneous. So if delta H is positive and delta S is negative, then delta G is always positive. If, on the other hand, delta H is negative and delta S is positive, then delta G is always negative. So if it's exothermic and the entropy increases, then delta G is always negative. and the reaction proceeds spontaneously at all temperatures in the direction as it's written. Those are the fun ones, right? Because those are always there. But we have these two other cases where if it's endothermic, but the entropy goes up, sometimes that happens. The reaction proceeds spontaneously at high temperatures. Now, why high temperatures? Well, that's because we have to make this negative T delta S bigger, okay? So that's what we need. We need this to be the bigger factor than this delta H to make delta G be negative. So high temperatures, this will work. If, on the other hand, delta H is negative and delta S is negative, so it's exothermic, but my spontaneity is going down, the reaction proceeds spontaneously at low temperatures. So now I want my delta H to be the bigger factor, and I want this to be limited. So low temperatures when that's going to happen, and delta G is going to be less than 0. Okay, so those are our conditions. One of the things that you will be asked to do is to tell me what signs of delta H and delta S are always positive, or always spontaneous, never spontaneous. How do we solve for the temperature at which this reaction will be spontaneous? So those are things that you're going to need to be able to do with that. So you're going to need to be able to look at what's the relationship there. All right. You may get asked something like, if delta H is positive and delta S is positive, what do you need to know about the temperature to know that this is going to be a spontaneous reaction? Okay, so there we'd be looking again at low temperatures for that. So that's what you need to be able to do with that information. Okay. All right. So you will need to be able to calculate delta G in terms of the delta G values as they're given to you, or once you've calculated delta H and you've calculated delta S, then you need to be able to calculate delta G. All right. So we can set all of this and we can find the temperature at which this will change. So we know that delta G is going to go from negative to positive. It's negative when it's spontaneous, it's positive when it's non-spontaneous. If we want to find out where that temperature is, where that changes, then we can do that, all right? And we can solve for that. That is something that you may be asked about. Okay, so you need to be able to solve for that particular temperature, all right? Now, phase transitions and free energy. Because the temperature is constant during a phase change, free energy is 0 because the system is at equilibrium. All right. There is a large change in spontaneity in these processes, however. So to go from more ordered to less ordered, it's a negative entropy, less ordered, and therefore is favorable. Okay. We can measure the molar heat of the change using delta S equals delta H over T. We can go from less ordered to more ordered. That's a positive entropy, and thus unfavorable. This will be equal in size, but opposite in sign to the molar heat measured above. Bear with me just a moment, I apologize. Sorry, guys, I confused myself. It happens. All right. So, questions, comments, problems about phase changes and whether they're spontaneous or not. All right. Again, going from less ordered to more ordered is bad. More ordered to less ordered is good. Okay. So remember that the entropy is the only thing that you need to consider in phase change. Free energy and chemical equilibrium. So the relationship between free energy and under non-standard conditions and standard free energy is this right here. delta G equals delta G naught plus RT ln of Q. Okay, this looks very familiar because this looks very similar to what we saw for our delta H and our delta S and what we saw with the E cells. Okay, so this is the same kind of thing. A large negative value of delta G will tend to make delta G also negative. The reaction will proceed from left to right until a significant amount of product is formed. And a large positive delta G will tend to make delta G also positive. So the net reaction will proceed from right to left until a significant amount of reactant has been formed. Okay. So at equilibrium, delta G equals 0, Q is equal to K. So delta G naught equals minus RT ln of K. We talked about that. We talked about this when we were talking about our E values. So the following relationships exist between delta G and K. So if K is greater than 1, right, we favor forward reaction, okay. The ln of K is positive, the delta G is negative, products are formed over reactants at equilibrium. If K equals 1, the ln of K is 0, delta G is 0, products and reactants are equally favored. And for K less than 1, then ln of K is negative and therefore delta G is positive. Reactants are favored over products at equilibrium. Okay, so delta G 0 is here, all right? We're looking at the pure reactants and the pure products. If delta G is higher for the reactants than it is for the products, and that's a negative delta G overall, okay, less than 0, that's spontaneous. If our delta G for our reactants is lower than for our products, that delta G is positive, and that is therefore not spontaneous as we move forward. Now we can look at, here's the overall delta G. So delta G equals the products minus the reactants. That's bigger than 0 here. We can see Q is less than K in this portion of the graph. Delta G is less than 0 in this portion of the graph. We have Q is equal to K at that dip because that's where our equilibrium is. Okay, so delta G is equal to 0 at that point. Where Q is greater than K, delta G here is greater than 0, okay, that's going to be this up curve here. So you should be able to look at that in both sets and tell me whether Q is greater than K or Q is less than K based on what you're looking at. So you should be able to describe these relationships to me based on these graphs. And given one of these graphs, point out, where would we calculate delta G? Where do we see the changes? Where is Q less than K? Where is Q greater than K? Where does Q equal K? And based on what you see, is this spontaneous or non-spontaneous? Okay, so that's something that you should be able to do. Questions, comments, problems on that? No? All right, fine. So like I said, we will give you practice in calculating what is delta G, what is delta H, what is delta S, using the equations that we've looked at. How do I calculate delta G once I've found delta H and delta S? How do I find the temperature, which this is spontaneous or non-spontaneous? All of those things are things you should be able to calculate, and I will walk you through how those things, some samples of those calculations, and what those questions might look like, and how they might all tie together. All right, because that's what's important for me, is that I can see that you guys can tie those concepts together. So one, I want to look for the concept. Do you understand the concept? But also, how do those concepts tie together? Because that's the part that really matters when we're talking about this. Okay? So questions, comments, problems. Hopefully there's nothing that you guys have questions, comments, or problems about. But if you do, let me know. Email. Come to my office hours. Come to my office. Give me a call. Let's talk about it. All right? I will see you guys soon. I hope you had a great semester. Thanks for sticking with me. Bye, guys.